Welcome to another video of Roland Mösel, founder of Planetary Engineering Group Earth. The iron-air battery and the possibilities of this new battery development for autarky and summer-winter balancing. First, the aims of the Fraunhofer Institute, which develops this new battery, 250 watt-hours per kilogram, at last 60% efficiency and 500 full charge-discharge cycles. This is really enough because this battery is not aimed for day-night balancing. For day-night balancing, the efficiency is far too low. It's aimed for summer-winter balancing, and for this purpose, the competition is completely different, and 60% is a real high efficiency for this purpose. It should cost about 10% of a lithium battery system and has first advantages. It's insensitive to overcharging and deep discharge, so no big burden for the battery management system. First we look off-grid. Somewhere is a house. Here we have the standard size of the GEMINI next generation house, and it's far away from the next grid connection, and so the people decide to be off-grid. I made here already another video. I assume 600 kilowatt hours per month consumption. Yes, the consumption is so high because there are also the electric cars of the family who has to be charged. And we assume for each location and for each month additional electricity consumption for room heating and room cooling. Yes, in Cairo there is a lot of room cooling necessary, while in Oslo we are only on the side of room heating. And we make an energy balance of this, and we see south of Vienna we don't need summer-winter balancing, and when we go to the north, this is more and more a big theme. For the first, I would say for Vienna, take 1000 kilowatt hours of iron-air battery, in Berlin 2000 kilowatt hours, and in Oslo 4000 kilowatt hours. These are 4 tons, 8 tons, 16 tons of battery, or in Oslo, the battery is about the same weight as the house has. In the video about summer-winter balancing, I looked for hydrogen and fuel cell. Here we have 12 bottles for hydrogen, and this price is without value-add tax, and also missing is electrolysis, high-pressure pumps to fill the hydrogen into the bottles, and the fuel cell. So the end price is far higher, and in this huge thing is only 14 kilo of hydrogen, and when the fuel cell has only 39% of efficiency, these are only 175 kilowatt hours of electricity. With 250 watt-hours per kilo, we would need only 700 kilo of iron-air battery to do the same. Not exactly the same, because the efficiency of the iron-air battery is far higher, 60% or maybe even above. And here I have the efficiency of electrolysis. I have to power the high pressure pumps to put the hydrogen in the bottles, and I have the efficiency of the fuel cell. And all efficiencies have to be multiplied, and at the other end, maybe the fuel cell system has only 20% efficiency, so I need much more electricity to charge the system. So in this case, when 10% of lithium battery system price is available, this is far superior, and you can forget the hydrogen system. In another video I made a study, is Germany with 100% photovoltaic possible? And I made the simulation with original solar data from 2008 and made the following assumptions. 900 terawatt hours electricity demand netto, 1,400 gigawatt of photovoltaics, 4,000 gigawatt hours of batteries, 180 gigawatt of power to methane, 50 cubic kilometers of methane storage. Germany has already 25 cubic kilometers of it, and 80 gigawatt of combined cycle power plants. Here a little bit of overview about the costs and efficiency of this central big technique. Here we see the usage of combined cycle power plants and power to methane units. We see a time separation of this. In the winter half year I use combined cycle power plants, and in the summer half year I have enough electricity from photovoltaic to power to methane units to fill up the methane storage. Here's the methane storage. We see until spring it goes down, and in spring until autumn begin it goes up, and you see sometimes the curve up is steep. These are very sunny days, and sometimes the curve is very slow increasing. These are very cloudy days. And then comes autumn and it goes down, and at the end of the year 245 terawatt hours, or about 24.5 cubic kilometers methane are missing. This missing methane should be imported, and much more southern countries like Italy, Spain and so on have with the same equipment much surplus on electricity, and it's for them easy to produce the missing methane and export it to Germany. Now I make the same simulation with the much higher efficiency of the iron-air battery, and at the end of the year only 40 terawatt hours are missing. But the problem is, when I assume 80 euro per kilowatt hour of lithium battery, and this new battery type is only 10% as expensive as a lithium battery, then we are down to only 8 euro per kilowatt hour. But we have here 250 terawatt hours of batteries, and 250 terawatt hours batteries times 8 euro per kilowatt hours is 2,000 billion euros. So maybe there is a possibility to mix the both systems for a cost optimization. We have these two systems. We have decentral iron-air and central power to methane. Grid expansion. At iron-air we need nearly no grid expansion, but at central power to methane we need at last 3 times more grid, so we have a massive grid expansion. Power to methane units, 0 gigawatt at iron-air and 180 gigawatt at central power to methane. Methane storage, at power to methane we need 50 cubic kilometers of it. Iron-air batteries, we need 250 terawatt hours of decentral iron-air, or 0 of it at central power to methane. Combined cycle power plants, we need nothing of this at decentral iron-air, but 80 gigawatt at power to methane. Electricity import at iron-air is 40 terawatt hours. Methane import at power to methane is 245 terawatt hours. And now we search for the optimum mix to have the best cost reduction possible. Here on the x-axis I have power to methane units, 180 gigawatt down to zero. At 180 gigawatt power to methane I have zero charging for the iron-air batteries. And when I go down to zero power to methane units, I have about 320 terawatt hours for charging the iron-air batteries. And we look in the middle of it, at 80 gigawatt power to methane units, I have enough terawatt hours left to charge 50 terawatt hours of iron-air batteries. And the advantage of this is I have 100 gigawatt less power to methane units. These power to methane units cost money. And instead of this, I have 50 terawatt hours of iron-air batteries. And the big advantage is that I don't need a big grid extension, and I show now why. Grid connection of a typical small village of 100 small houses. Each house has a 25 ampere 3-phase connection to the grid. This is 17 kilowatt, but all the 100 houses are only connected by a 400 kilovolt ampere trafo station. And 400 divided by 100 is only 4. How can this work that they promise everybody you have 17 kilowatt, but in reality it's only 4 kilowatt and everybody at the same time? Yes, the problem is at the same time. It's not very properly that in all the kitchens, all the hot plates and the baking oven are turned on at the same time. When this would happen, sure, the grid in this small village would go down. But because the probability that this happens at the same time is very low, they take only a 400 kilovolt ampere trafo and everybody is happy. But there are new things, electric cars and photovoltaic. And in photovoltaic, it's not so that half the village has sunny weather and the other half of the village is under heavy clouds. This does not happen like this in weather conditions. So we look now what happens. We are talking here about climate protection superiority houses, and they have very much photovoltaic. Let's have here only an average of 40 kilowatt photovoltaic per house. And when they would all dump the electricity from the photovoltaic direct to the grid, this could be 3 megawatt, about 75% of the maximum, because it's east-west roofs, and so we have 75% of the theoretical maximum of the installed photovoltaic. Or we would have here a very massive necessity for a grid extension. Here we assume, in addition to the 40 kilowatt photovoltaic, 120 kilowatt hours of lithium iron phosphate batteries. We assume a maximum yield day of 6.5 times the installed photovoltaic, so 40 times 6.5 is 260 kilowatt hours. And we assume 20 kilowatt hours in average of own consumption. Yes, we have to charge our cars. And in this case, the whole village will deliver 24 hours, equally 1 megawatt. But sorry, the trafo is still only 0.4 megawatt, and we still need a huge grid expansion to do this. And now we try it with the iron-air battery in addition. We have the same per house, but in addition we install 1,500 kilowatt hours of iron-air batteries, and because they have only 60% efficiency, we need 2,500 kilowatt hours to charge them. And then we have again this maximum yield day, where our photovoltaic delivers 260 kilowatt hours. In this case, we charge the iron-air battery with 144 kilowatt hours, and when the whole village does the same, we have 0.4 megawatt delivered, and the draft has 0.4 megawatt. Now it works without grid extension. This is the value of the iron-air battery, that we have here no grid extension. And what we do with the stored energy, we will deliver it in winter time. There are at every day fluctuations how much power is needed for the grid. In the winter, we can use the combined cycle power plants continuously at 100%, all the day the same power, and the ups and downs of the power we can deliver with the iron-air batteries. So we have not to change the power output of the combined cycle power plants so often. We can use them for months at the same power level. And this could be that about 20% iron-air batteries and 80% power-to-methane could be the cost optimum of the system. Now let's look at an average day. At an average day, 0.3 megawatt are delivered to the trafo and 0.4 megawatt has the trafo. This means up to 133% of an average yield day can be handled by the grid alone. And when a day has more photovoltaic yield than 133% of an average day, the additional power goes to the iron-air batteries. And because we need 2,500 kilowatt hours to charge 1,500 kilowatt hours of iron-air batteries, this happens in all the summer, and at the end of the summer the iron-air batteries should be fully charged and can deliver the energy back in the winter half year. The aim is the planet renovation. This means minus 250% CO2 emissions until we reach again 350 ppm. And this means that we take massive amounts of carbon out of the air. When we took only 33 gigatons of CO2 out of the air and split it in carbon and oxygen, these are already 9 gigatons of carbon, a very big amount of carbon. Let's see what we have else here. We have concrete and steel, and the theory is this will replace the steel industry and the aluminium industry because we can make all with carbon fibre. We make bridges with carbon fibre, we make cars with carbon fibre, and what happens to all the iron industry? It would not be good if such a big industry would completely vanish. And with the iron-air batteries, the iron industry has a complete new task. Not building cars and bridges and all the things we make today from steel. Now the task is to make enough iron-air batteries to have a good summer-winter balancing for all the civilization. But it's only most necessary far away from the equator. When we go more close to the equator, we don't need summer-winter balancing, but in the north, far in the north, like Austria and Germany, we need it very big. The next is the general requirements for climate protection superiority houses. When this battery hits the market at the price of 10% of lithium battery systems, this will influence what the standards of a climate protection superiority house are. I just published a video about the replication factor. This means I need energy to build the house, and the house needs energy for the household, for domestic hot water, for heating and cooling the house, and for the electric cars of the inhabitants. And in addition, the house should deliver enough energy to build up the same house again and again. And this again and again is the replication factor. And this could be when the iron-air battery hits the market really at these conditions and at 10% of the price of a lithium battery, we could change this replication factor to replication 1 and continuous energy delivery. This means the house should deliver in these 30 years enough energy to build again the same house, and in addition it should export enough energy, and how much, this is the replication 1 export factor. This was another video of Roland Mösel, founder of Planetary Engineering Group Earth. And as always, like, comment, subscribe, and hit the bell to be notified when I make my next video.